In this video, we're going to look at the effectiveness NTU method, and we're going to have to define certain things. We're going to define the capacity rates. A capacity rate, the capacity rate for the cold and hot fluid can be defined this way. They're defined like by a capital C. So I'll put it like as a capital C. Let's say for the uh, let's say for the cold fluid is going to be the mass flow rate of the cold fluid times the heat capacity, specific heat of the cold fluid, and the capacity rate for the hot fluid is going to be the mass flow rate of the hot fluid times its specific heat and constant pressure, like this. So again, this is the mass flow rate of the cold, specific heat and constant pressure of the cold, mass flow rate of the hot, specific heat at constant pressure of the hot fluid. Again, this is capital C sub C at capital CH. And then uh, usually one of these will be bigger. So the largest of these two is called C max, and the smallest is called C min. And then we're going to also have the ratio of the heat capacity rates. And that's going to be again capital C star. And it's simply the C min divided by the C max. I'm making the C's kind of funny just to emphasize these are capital C. Now, heat transfer, whether it be cold or the hot, we've defined it before, but now it can actually be defined by epsilon times what is called Q dot max. And Q dot max is going to be C min times the hot fluid in minus temperature of the hot fluid, excuse me, the cold fluid in, like this. So this would, Q max is this part right here. So this is actually Q max. So that'd be kind of the maximum possible heat transfer. Again, that'd be Q dot max, I should say. And your heat transfer for any specific case is going to be uh, epsilon times this. Again, epsilon is called effectiveness. And epsilon is what's called effectiveness. And we're going to calculate that a little bit later, but I'm just introducing some of these definitions right now. I'm going to also introduce a non-dimensional variable called the number of transfer units. Or NTU, and NTU is going to be equal to the overall heat transfer coefficient times the tube area divided by that C min. We talked about C min a few seconds ago. Again, U overall heat transfer coefficient. And A would be like, say, the tube surface area. And C min we mentioned a few seconds ago. Again, it's going to be the smaller of these capacity rates. Now, one thing I should have noted, um, going back to this C min and C max, I should note that if one of the fluids stays at constant temperature, then its capacity rate is going to approach infinity. Then that fluid becomes the C max. And what happens, and we won't get all the details now, but what happens is that C max in that case will go towards infinity. And then again, since that's in the denominator here, then C star, the ratio of capacity rates, is going to be 0. Again, that happens if you have like a fluid that's staying at a constant temperature. Again, that fluid will be the C max, and it'll in effect be go to infinity, and then C star will be 0. This will usually happen in a case when you have, let's say, a fluid condensing from a saturated vapor to a saturated liquid. But that's going to come up here shortly, so I should note that. Again, if you don't have something at constant temperature, the C min and C max are all calculated this way. Again, usually we're going to have to look up effectiveness in the table. Again, using C star and NTU. However, if C star is zero, as I mentioned before, that's going to be the case if one of the fluids is at constant temperature, then again, for the specific case when C star is zero for effectiveness, we may use this equation here. This is going to be like the exponential E raised to the negative NTU. We can use that in this specific case of when C star is zero. Let's take a look at this problem. Saturated vapor at 130 degrees C enters a shell and tube heat exchanger. The heat exchanger has one shell pass and two tube passes and has a surface area of 0.75 square meters. In the heat exchanger, saturated vapor condenses to saturated liquid. The overall heat transfer coefficient is 2,500 watts meters squared K. Cooling water is what's going to cause the steam to condense, and cooling water enters at zero point 0.6 kilograms per second and 18 degrees Celsius. So let's take a look at this. And so some questions. What is the heat transfer rate to the water? That would be the heat transfer rate to the water from the steam. Again, it's going to have the same value as the heat transfer rate from the steam, except the steam will have a negative value. What is the final water temperature? And what is the mass flow rate of the steam? So let's take a look at this. So I'll make a little picture here. Again, we have, as I mentioned, saturated vapor. And it's coming in at 130 degrees C. And then water is also coming in over here. So this would be, I guess we can call this the shell in. So you can call, I guess we can call this one T shell in, or also you can call it T hot in, depending upon which kind of notation you want to use. And then this is going to be the shell out. And then we're going to have the water's coming in. So it's going to be the T tube in. And that's the same as the T cool in. And that's going to be at 18 degrees C. And the mass flow rate of the cool fluid is going to be 0.6 kilograms per second, like this. And we're told that the tube area is 0.75 meters squared. The overall heat transfer coefficient is 2,500 watts meters squared K. And also, I looked up ahead of time in the back of the book for water. The heat capacity for the cold or for the water is 4.175 kilojoules per kilogram K because we're going to need that. And so let's start by calculating Q max. As I mentioned previously, Q max is going to be this C min times this THI minus TCI, T hot in minus T cold in. Now, what's C min going to be? Well, notice this is condensing from a saturated vapor to a saturated liquid according to the problem. And so that means, so out here we're going to saturated liquid, and the temperature is going to be constant. So the shell out, which is same as the TH out, is also going to be 130 degrees C. So again, since the steam is a constant temperature, then as I said before, that the hot fluid is going to be your C max. Again, we said if it's ever at constant temperature, it's going to be C max, and also it's going to approach infinity. And also your C star is going to be equal to 0. We know those ahead of time. So now we can calculate our C max, Q max, and our Q max was going to be equal to our C min, according to the formula I showed you, and then THI minus TCI. Again, because C max, that was the hot fluid, so therefore T min is going to be the cold fluid. So this is going to come from the water. And then Q max is going to be, again, remember what that is. That's going to be CP for the cold times the mass flow rate of the cold. I think I flipped the order a little bit from what I showed you before. And it's going to be THI like this. And in our case, according to our problem, the mass flow rate of the cold is 0.6, and the specific heat at constant pressure is 4.175 kilogram K. C is 0.6 kilogram per second. Again, T hot in was 130. And T cold in was 18. And again, the difference is the same whether it's degree K or degree C. And so now down here we have a K, so I'm going to put, since that difference is going to be the same, you can call it C or K. Maybe I'll call it C, but just remember it's a difference, so it'll be the same there. And so we'll put this in our calculator. And the number I got is 280.6. And let's check our units. Kilograms cancel. K's will cancel, so it's going to be kilojoules per second is what we would expect for heat transfer. So we have the heat transfer. Again, I should emphasize this would be the max possible heat transfer. In other words, if everything was perfect, again, this is max possible. And we'll have to multiply this by our effectiveness to find the actual heat transfer. But we have to now find the effectiveness. So let's actually calculate that. For the effectiveness, we're going to need NTU, and so we'll go ahead and calculate that. That's UA divided by C min. And we were given the overall heat transfer coefficient, which was 2,500 watts. And now actually, I'm going to convert that. So that'd be 2.5 kilowatts. The 2,500 watts would be 2.5 kilowatts. And kilowatts are kilojoules per second. I want to put that in because some of the other units are in kilojoules. And again, it was kilowatts over meters squared K. Excuse me. Yeah. So it'd be 2.5 kilowatts over meters squared K, which same as 2.5 kilojoules per second over meters squared K. And then our area is 0.75 meters squared. And again, we want to divide this by C min. C min is just what we had a second ago. That was the CP times MC. So it would be the same values again. Like this. And I'll put that in my calculator. And when I put in my calculator, I get something like 0.749. It's supposed to be dimensionless, so let's just check our dimensions. Meters squared canceled, kilojoules per second uh, canceled because we have kilojoules second here, kilojoules second here. Yeah, as I said, kilograms canceled, meters squared canceled, and then finally the Kelvin, when we do the reciprocal here, is going to cancel. So we have this. Now again, often we'll have to look up this in our table along with our C star. Now in this case, again, as I mentioned, uh, our C star is going to be 0. And when the C star is 0, we don't have to look up in the table. We can actually use an equation. And to find effectiveness, so the effectiveness is equal to 1 minus the exponential, that'd be like e to the negative 7.49, like this. So that's going to be, that's our NTU. I should have written the equation separately up here. So it's going to be EXP to the negative NTU. That's the equation you can use when C star is 0. You can use this. So when we substitute our NTU into here, we get this. And we put that in your calculator to get effectiveness of 527, like this. And actually, right here, I could also calculate the actual heat transfer rate. So, because we found our Q max, was 280.6. So the actual heat transfer rate, say, to the water, again, we said that was going to be E times Q dot max, like this. And of course, this is the effectiveness, 0.527 times our Q max, or 280.6 kilojoules per second. And that comes out. And that's going to be 147.9 kilojoules per second. Again, that's the heat transfer rate to the water. Now that's going to be the same as the heat transfer rate from the steam, except it'll just be have a negative sign. So we can either, uh, again, just keep in mind that the effectiveness times the Q max is always going to give us a rate of heat transfer. And again, we use that again when we calculate the heat transfer rate from the steam. So now, is I had earlier, I said that the actual heat transfer, and some books actually call this actual, but I'll just put Q, is going to be equal to, like this. And now we're actually looking for now the final temperature of the water. But now, again, for the water, again, this would be the heat transfer rate of the water. Remember, for water, you can use M for the cold, CP for the cold, delta T. And for delta T, I'll just put T2 minus T1, be a little bit easier. So again, that's calculating the heat transfer rate of the water with CP, M dot CP delta T. Then over here we had this. Again, so we use the fact that the heat transfer rate is equal to efficiency times Q dot max. And then, because this is water, we can use M dot Cp delta T. Again, we want to solve for T2. So we'll divide these over here. So divide by these. So after I divide by these, I'll add T1 to both sides. So then we can calculate T2 this way. Because we know Q dot max, and we know the effectiveness. So the effectiveness was 0.527, and Q dot max was 280.6. And then the M dot C for the cold was 0.6. And for the cold, our CP value was 4.175 kilojoules kilogram K, like this. And then our T1 for the cold. I should probably have put in cold for these temperatures. But the T1 for the cold was 18 degrees C. Well, I put that on my calculator. I got 77 or 77.03 degrees C. So that's the final temperature of the water. And let's see, what else do we need to find? We're going to need to find the mass flow rate. And we know that the heat transfer from the steam is going to be equal to the heat transfer rate to the water, except the opposite sign, of course. Because whatever heat transfer there is to the water, it's being taken away from the steam, so there'll be negative. And so we can say then the Q dot steam, a value again we know is going to be uh, m dot delta H. Now again, for air or water, we could use CP delta T. But again, since this is steam, we can't do that. We have to use the steam tables. And so that's going to be m dot. And it's going to be H2, of course, minus H1. And then again, just to show all the steps, don't have to show all these steps, but I just want to be sure everyone understands. In our case, it's vapor condensing to water to saturated liquid. So that means H2 is going to be H sub F, and it started out as saturated vapor, which is going to be Hg. So if we want to find the mass flow rate, we'll just solve for this. Like this. And then finally, we know that that Q dot steam was going to be our epsilon times our Q max. And again, our epsilon times Q max. Q max we calculated to be 280.6 kilojoules per second. And we'll have to look up in the steam table. Uh, again, this is going to be, these are both going to be at what, 130 degrees C. So if we look up in the steam table, and when I look at the steam table at 130 degrees C, I get that HF was 546.31, HG was 2720.5. Oh, by the way, since we're dealing with the steam, heat was transferred away from the steam, so this should have a negative in here. So let's put this in our calculator. And so I'm coming up with a mass flow rate of the steam of 0.068. And that's going to be kilograms per second like this. So that's the mass flow rate of the steam.